I'm Dan Johnson, the lead scientist for the STEM Writing Project. I want to tell you why we launched this project and how pieces of our six-element model work together to support students as they develop their scientific writing skills. Now, I've been teaching and training others to teach scientific writing for 25 years, so I've watched a lot of undergraduates struggle to learn this vital career skill. I've also seen firsthand how hard it can be to make meaningful writing experiences a part of introductory biology. That's why my project team and I created a 6 elements method. First, we asked a lot of questions. What are the resources and guidance that students need to learn scientific writing? And what are their barriers? Which barriers make it hard for teachers to include writing in large enrollment courses? And what can we do to make it easier? What does research say are best practices for teaching scientific writing? What can STEM teachers learn from full-time professional writing instructors? And are we doing anything that actually gets in students' way? How can we evaluate students' development as writers, not just individually, but over an entire program? What we've learned, and our answers to the biggest of these challenges, is what the 6 elements model is all about. From our colleagues in the first-year writing program, we learned that students have almost no experience reading scientific literature, so most have no idea what the structure or goals are. To address this, we began by having students read basic scientific articles before they tried this genre themselves. We learned that different teachers have different goals and expectations. As a result, students get different messages about how to write well. Most important, students do not know why we write a particular way, so scientific writing becomes a set of arbitrary requirements. In response to the last 2 challenges, we created an open-source biology writing resource guide. It's designed to be used in multiple courses, so students can have one clear set of guidelines. It explains why scientists write in a particular style, how the pieces come together, and what goes where. We've also included detailed case studies with full data sets and examples of well-written and poorly written lab reports. The second big lesson we learned is that teachers, and especially graduate teaching assistants, need as much training and practice as their students do. SEM's teacher training includes formal workshops that introduce our methods and practice grading sessions where multiple instructors score reports that have been pre-selected with particular errors. Student training activities include collaborative reading and annotation of published articles and peer review of current and prior student reports. We also learned that students overestimate their understanding of scientific writing requirements. That's why diagnostic activities are important. They surface student misconceptions so instructors can adjust how they teach to address their students' specific knowledge gaps. We try to collect our diagnostic data as part of regular student training activities and assignments so we can get more meaningful data. We also use diagnostic activities to monitor student progress over time. Originally, we included automated support in SEM to streamline routine data collection, but we soon learned that it also improved student performance. For example, we require students to use the SawWet web form to submit their reports. The form will not accept a report with a required section missing if it does not have citations or it does not have summarized data. Before we launched SawWet, up to 22% of students in our historical control group submitted incomplete lab reports that ultimately earned a score of unacceptable. Just 1 year after introducing the web form, incomplete lab reports dropped from 22% to less than 5% of initial submissions and less than 2% for revised reports. Our web form also standardizes report formats. That lets us use data science tools to extract information from hundreds of writing samples at one time. Our 6 elements model also uses bins-based scoring rather than points-based rubrics. Student writing is given a score of 0 to 4 corresponding to a general description of its overall quality, not a points-based rubric. Each score is based on binary requirements that are either present or absent, so different instructors can't deduct different numbers of points for the same errors. We have 5 basic criteria that must be present for a student to earn a minimum acceptable score. Students can earn higher scores if their work does not contain either writing and logic flaws or technical flaws. Regardless of the score earned, students get reflective, coaching-oriented feedback on what can be improved. Now, reflective coaching began with an observation that graduate TAs often spend 30 to 60 minutes or more making detailed copy corrections and annotations on lab reports, only to have students make a few minor fixes and ignore the larger problems. We learned from writing program instructors that copious copy editing is usually ineffective. Instead, students learn more quickly when they get fewer comments, and when those comments encourage self-correction. In response, we designed a framework for commenting on student reports and trained GTAs to use it instead of freeform commenting. This method greatly reduced GTA workload and focused students' attention on the most important revisions. Bins-based grading plus reflective coaching-oriented feedback shifts the conversation away from a points harvesting mindset so teachers and students can talk about how to improve instead. In summary, our 6 elements model has reduced many of the challenges that we face when teaching scientific writing. Browse through our resources and see if our approach might work for you too.